learn like a pro.
All right, today we're going to zoom way in. I mean, down to the microscopic level to uncover the secret architecture that builds everything around us. Yeah, everything. The device you're watching this on, the water you drink, the very air you're breathing. It all boils down to one simple, brilliant idea. So, let's dive in. So, let me ask you a question to get us started. What could a solid steel beam, a puddle of water, and the air you breathe possibly have in common? I mean, they seem about as different as you can get, right? But believe it or not, there's a fundamental principle that connects them all. And here's the answer. They're all made of the exact same stuff. Countless tiny invisible particles that are always, and I mean always, moving. They're constantly jiggling, bouncing, and zooming around. That one simple fact is the key to, well, pretty much everything. And this powerful idea has a name, of course. It's called the kinetic particle theory. Now, don't let the name scare you. It's super simple. Kinetic just means motion. And particle, well, that's those tiny building blocks we're talking about. So it's really just the moving particle theory, a model that says all matter is just a huge collection of tiny things in motion. Simple, right? But it explains so much. Okay, so if everything is made of the same moving particles, you've got to be asking, why does stuff look and feel so different? Why is a rock hard and air not? Well, it all comes down to the architecture, how those particles are arranged and how much energy they've got. Let's look at the three main blueprints. First up, solids. In a solid, the particles have the least amount of energy. I want you to picture them like a perfectly arranged audience in a theater. They're locked into this neat repeating grid by really strong forces pulling them together. They can't just get up and wander around. But, and this is key, they're not perfectly still. They're constantly vibrating in their fixed spots, kind of like they're fidgeting in their seats. Okay, now let's add a bit of energy, maybe some heat. What happens? We get liquids. So back to our audience. The show's over, and now it's a crowded party in the lobby. The particles have enough energy to break free from their assigned seats. They're still packed in pretty tight, but now they can slide and jostle past one another. They're constantly moving and changing neighbors, and that's exactly why liquid can flow and take the shape of whatever you pour it into. And finally, what happens when you add a ton of energy? You get gases. Now, this isn't a crowded party anymore. This is like a few people with endless energy in a gigantic, empty stadium. They've absorbed so much energy that they've completely broken free from each other. They're super far apart, zipping around at incredible speeds in random directions, bouncing off the walls, and filling every inch of the space. So we have our three particle arrangements: the rigid grid, the sliding crowd, and the free-flying speedsters. But here is the truly amazing part. This invisible, microscopic architecture is what creates all the properties of the stuff we see and touch every single day. And this is where it all just clicks. You ever wonder why a solid has a fixed shape? It's because its particles are locked into that rigid theater seating. And why can you squeeze the air in a bicycle pump? Because a gas is mostly empty space. You're not actually squishing the particles, you're just closing the massive gaps between them. See, the big picture properties come directly from the small picture architecture. But look, this isn't just some neat idea you learn in a classroom. Understanding how these particles behave is absolutely crucial in the real world. In fact, getting it right can be the difference between a brilliant piece of engineering and a total disaster. Let's take a look at a steel railway track on a scorching hot day. The sun is just blasting it with thermal energy. Now, if we could zoom into the particle level, we'd see our little theater audience getting really fidgety. They absorb that energy and start vibrating like crazy, pushing and shoving against their neighbors, demanding more elbow room. The whole structure has no choice but to get bigger, to expand. And this is where the genius comes in. Because engineers know all about this particle behavior, they plan for it. They intentionally build these small but absolutely vital expansion gaps between sections of the track. This gives the metal a safe place to expand on a hot day so it doesn't bend and buckle out of shape, which could be catastrophic. It's a perfect case of micro-knowledge solving a massive macro problem. So, you see, the kinetic particle theory is so much more than just a theory. It's a fundamental blueprint for how the physical world works. It allows us to predict how materials are going to act and helps us design and build pretty much everything around us, from bridges to buildings, safely and smartly. So I'll leave you with this thought. Now that you've seen the hidden architecture, this invisible dance of vibrating, sliding, and flying particles that's happening everywhere all the time, what else in your world does it suddenly explain? Once you start looking, you'll see the answers are all around you. Thanks for joining me.